Hello everyone. So in this video I'll be talking a little bit about the Lambert W function. But in order to understand it, we kind of need to dwell a bit deeper into what a function is, first of all. So you can imagine function to be kind of some sort of machine. So let's say that we have a machine here that has two ends. So let's say that that this is our function right here. So here we have a function. And what a function does is that it transforms whatever we put into it. So for example, we have two. So let's say that this is some type of unknown function, and we were to put it inside this machine, then it will output a number. And in this case, it became 4. And let's say that we input another number, so for example 3, and this time it outputs 9. Now this is essentially what a function does. It basically accepts an input and then it gives us an output. That's all that a function essentially is, you can say. And a rule for a function, which I think you've learned, is that a function cannot have two different outputs, because that wouldn't necessarily make sense, since then if we were to have an input, then it has a risk of having two different outputs, which doesn't really make a lot of sense. But in theory, this is all that a function does. It transforms any value that we put into it. And we often represent it as, for example, f of x, for example, and we often define that function with an equal sign. So we can, for example, define f of x to be equal to x squared. So you can imagine this to be our machine here, but this time our machine, what it does is that it transforms any value that we put into it by squaring that number. So that's what f of x equals x squared means. It basically means for any arbitrary input x that we choose, it will just spit out an output x squared. So in this case, for example, if I have 9, so let's say that this is our f of x, then it will output 81, because 81 is 9 squared. So that's all about functions. Now, whenever we talk about functions, we also tend to mention a little bit about inverse functions. And what an inverse function does is, well, it transforms an output to an input. So let's demonstrate it with the same illustration as I had before. So we imagine this machine or box that will be our function. And let's say we don't know what this function is, but if we have, for example, an input 8 and it spits out an output of, for example, 40, it doesn't matter, then how can we reverse this process? So for example, if we have an input of 8 and we got an output of 40, but how can we uniquely identify our input by knowing an output? So let's define this function. So let's define this as g of x being equal to, let's say, 2x. In that case, for example, if I have 9 and it outputs 18, then we know what the output will be. But let's say we only have 18. We only have the information that 18 is our output. Then how can we determine what the input was? Well, in that case, we just look at our expression, g of x equals 2x, and we see that our g of x, 2 times x, has to be equal to 18. So, in other words, x has to be equal to 9. So our input, or our initial input, had to be equal to 9. So what an inverse function does is that it kind of reverses this process of transforming or transformation. Basically, if we have a function and we want to know what input corresponds with our output, then we use an inverse function. So in this case, for example, we have our function to be equal to 2x. The inverse function is basically which we denote as our function to the negative 1 of x. So that's going to be the inverse of g of x. It's going to be equal to x over 2. And that makes sense because if I have an output of 2x and I were to input it into this function, you'll see that it just becomes equal to x. So, for example, g of negative 1 of our function, that just becomes our input. And as such, our inverse function g of x, the inverse function of g of x, is going to be equal to x over 2. And for example, if I have another function, h of x, so this function, for whatever input we put into it, it will output e to that power, that the input to the power of the input that we have. And the inverse function in that case will be natural log of x, because if you think about it, by definition, if you have an output, h of x being equal to e to x, then if we were to put it into our inverse function, basically, if we have an inverse function and we have the function as the input of that inverse function, it must be equal to x, because as I demonstrated earlier, an inverse function basically reverses a transformation or an output that we have. So in this case, the inverse function of e to the x, or h of x equals e to the x, is just equal to ln x, or natural log of x. And it's simply because, well, natural log, which is our inverse function, of our initial function e to the x, that's just going to give us the input again that we initially have. So that's the concept of inverse functions, and that's pretty much all that we need to know in order to understand what the Lambert W function is, because the Lambert W function is just the inverse of let's say so the Lambert W function of x is essentially just the inverse of so it's essentially just the inverse of x times e to the power x. So what that means is, if I define a function, let's say it equals c of x, perhaps. So let's say that c of x is our function and it's equal to x times e to the power x. Then the Lambert W function, what essentially tells us is that since it's the inverse of this of x times e to the x, the Lambert W function of this function will just give us x. So it's just the inverse of x times e to the power x. So in other words, the Lambert W of x times e to the power x equals x. So yeah, that's what the Lambert W function is defined to be. And it's quite useful since it allows us to solve quite non-standard, unconventional equations. Since, for example, if we have 2 to the power x equals x squared, normally you wouldn't be able to solve that algebraically. That is to say, you probably won't be able to algebraically solve for x. And it's simply because out of the tools that we have, we cannot simplify this equation to the point where we have a clear value for x. So in this case, we are actually forced to use the Lambert W function to solve it, I guess you can say, in an algebraic way. Because the Lambert W function does not only apply to just x times e to the power x. If you think about it, if we have any equation of the form, any equation of the form where we have a function, so g of x times e to the g of x equals to some constant, a, then technically speaking, we will be able to get g of x by simply taking the Lambert W function on both sides. And you can do that, I guess, because you can make a substitution for our function, and it will practically work. So this becomes actually very useful when we solve these types of unconventional equations, because normally when we have these types of exponential equations, we are usually able to simplify them to an equation of this form. So w of g of x times e to the g of x is going to be equal to g of x, which is going to be equal to the Lambert W function of a in this particular equation right here. So let me demonstrate how to solve this particular equation. 2 to the power x equals x squared. So this won't include all of the solutions, but I will be showing how to get all of the solutions later on. But normally how you would solve this equation is, of course, you can guess, for example, x being equal to 2 or x being equal to 4. But to algebraically solve it, we can do something like this. So let's say that we take natural log on both sides. Then we have x times natural log of 2 being equal to 2 times natural log of x. And this basically comes from the, I guess you can say, rules of logarithms, or I guess you can say the properties of logarithms. And here, what we can do is divide by x, because what happens then is that we get natural log of 2 being equal to 2 natural log of x over x. But I can actually write x as e to the ln of x, because that just becomes, or I should add an implication sign, but natural log of 2 is equal to 2 natural log of x over e to the ln of x. And when I divide an exponent, I can simply just rewrite it as a multiplication, but with a negative sign here. So this becomes natural log of 2 is equal to 2 natural log of x times e to the negative natural log of x. And I can just divide by 2, because what happens then is we have natural log of 2 over 2 is equal to natural log of x times e to the negative natural log of x. And this is actually pretty good, because if I just multiply by -1 on both sides, you'll see that we get negative natural log of 2 over 2 is equal to negative natural log of x times e to the negative natural log of x. And you'll see that these two are the exact same functions. So we can just call them, for example, f of x, in which case we'll be able to use the Lambert W function and just get negative natural log of x back. So in this case, we can just take the Lambert W function on both sides, so like this, and that being equal to Lambert W of negative natural log of 2 over 2 And keep in mind, the Lambert W function is the inverse function of x times e to the power x, or a function times e to the, x times e to the power x. It's the inverse of that function. So here we can actually simplify this. So it's natural log of negative natural log of x being equal to Lambert W function of negative natural log of 2 over 2. And then we can actually solve for x because we just have a natural log on our left-hand side. So x is just equal to e to the negative Lambert W function of negative natural log of 2 over 2. And this does not include all the solutions. This is only one of the solutions. And there is indeed a method where you can find all three solutions, but it's somewhat complicated, I guess you can say. But because we haven't gotten there yet, I guess we can accept this solution for now. Now, here's a part where it gets a little bit more complicated. And the reason for this is because the Lambert W function actually has many different solutions for a single input. So, as an example, the Lambert W function of negative 1/10, that actually does not have a single solution. And the reason for this is actually, if you look at the function, so the function x times e to the power x on a graphing calculator, you'll actually notice that this function does not always have unique outputs. So it kind of looks like this, where it goes down and then up. This is, of course, a pretty inaccurate depiction of the graph, but it kind of looks like this. And you'll notice that there are certain parts where we have the same outputs but different inputs. In other words, our inverse function, which basically transforms an output into an input, would tell us that there are outputs, or there are inputs of the Lambert W function that can give us two solutions in the real numbers. And this is exactly true, because any number that is between negative 1 over e and 0, for any number that is between negative 1 over e and 0, if we plug that into the Lambert W function, there will be exactly two solutions. And the reason for this is, as I said, it's because there are the function, the main function x times e to the power x, can have different inputs but have the same output, which does not necessarily disqualify it from being a function, but it would mean that the Lambert W function in its whole, I guess you can say, is not actually a function. And for that reason, we often branch it into, or we often divide it into different branches. And I'm only going to focus on two. The negative first branch, so we depict that as w of negative 1 of x, and the zeroth branch, which is w of 0, which I think is the most familiar to everyone. And what this is basically the two real branches of the Lambert W function. And it looks somewhat like this. So this is what the Lambert W function, or at least the two branches combined, look like in a graphing calculator. And this is pretty interesting because this part right here that divides these two graphs, that's the part that is above here. So here is the x value negative 1 over e. So that's when when there begins to only be one solution, and here we have 0. So the line that divides the graph at negative 1 over e for the x value will define basically the two branches. The one that sticks out over here is the 0th branch, so the Lambert W of 0, or W0 of x, and the branch that goes down here. And as you can see, if I have an input, there are two different outputs. That's not necessarily what we want for a function. And as such, this is the negative first branch. So in the real world, or in the real numbers, we have two different branches for the Lambert W function, because we have a sort of interval where there are two different solutions, or two potentially different solutions. And for that reason, we divide it in different types of branches for the Lambert W function. And the thing is, there are actually an infinite number of them, because this function also extends to the complex numbers, but that's not something that I will be covering over here. So this is actually pretty interesting, since if we go back to our previous question, so e to the, where we have x being equal to e to the negative w of negative natural log of 2 over 2 here. So if you recall, we solved this equation, 2 to the power x equals x squared. We got this answer. We can this actually branches off into two different solutions, since negative natural log over 2 is actually between negative 1 over e. So it's between negative 1 over e and 0. And for that reason, it actually has two real solutions. But it still won't actually cover all of the solutions for this particular equation. It just gives us an algebraic alternative, I guess you can say, when it comes to solving these types of equations. But for our solution here, we actually get two solutions, that being x equals to e to the negative w0 of negative natural log of 2 over 2, which basically, we look down here, is within our 0th branch, so it's going to be the solution that is somewhere here. And we have another solution, namely the negative first branch, so that being x being equal to e to the negative Lambert W of negative 1 of negative natural log of 2 over 2. And this will include the solution that is at the bottom here, at the under here. So these two are the solutions that we got by using the Lambert W function. And I'm actually not so sure, but and you can check this on Wolfram Alpha, by the way, but I think these two actually get us 2 and 4 as our solutions. I can't necessarily recall, I might be wrong, and this might just be I might have mixed up things, but I recall that these two gave 2 and 4 solutions. And it's not quite surprising, considering that you could actually guess what the solutions are by just looking at the equations, and it's exactly these two. But there is one more solution to this equation, which is somewhere in the negatives, but with this method you won't be able to find it. But you can actually find the third solution by using the Lambert W function, but I won't be doing it here. And I will probably leave it as a challenge up to you. So let us take some examples for which we can actually use the Lambert W function. So a common example is basically whenever we have an exponential function being equal to some polynomial. So let's say 2x plus 1. So in this case, we have an equation that's not exactly solvable using our standard methods, standard algebraic methods at least. In this case, you will actually need to use the Lambert W function to solve it. And one way to do it is by using, for example, substitutions. So if I let y being equal to e to the power x, for example, then and there are definitely more simple ways of doing this, but this is the one that comes out of my mind right off the bat. But using this, we can get x. So y is equal to e to the power x. X is in that case equal to the natural log of y. And we can just substitute that in for our variables here. So y is equal to 2 natural log of y plus 1. And what I can do is I can actually move this here. And what I get is y is equal to 2, or the natural log of y squared plus 1. And then what I can do then is to subtract by natural log of y squared. And what I get is y minus natural log of y squared plus 1, or equals to 1. And y, I can actually rewrite that as natural log of e to the y. And minus natural log of y squared is equal to 1. And what I can do then is to, using the properties of logarithms, I can rewrite this expression as a natural log of e to the y over y squared being equal to 1. And now, what I can do next is to essentially raise e to the e on both sides. So e to the y over y squared equals e. And as I said, when we divide by an exponent here, we can rewrite it as y to the negative 2 times e to the y. Because y to the negative power is essentially just a division, if you think about it. So what we can do now is take the square root on both sides. Or actually, what we can do is to raise everything to the negative 1/2 power. And the reason for this is because when we do this, so we raise everything to the negative 1/2 power, we get something of this character. So negative 1/2 times negative 2, that's just equal to 1. And we just get something like this. Y times e to the negative y over 2 is equal to 1 over square root of e, because, well, negative 1/2, or raising something to the 1/2, is essentially just taking the square root. And when we take the negative 1/2 power, it's essentially just making it I guess you could say a division. And the final step is to multiply everything by negative 1/2. And what we get then is just this. We get negative y over 2 times e to the negative y over 2 being equal to negative 1 over 2 times the square root of e. So here you'll see that we have the same expression on the multiplication and the exponent, so we can use the Lambert W function on both sides to isolate the negative y over 2 term. So we get the Lambert W of -1 over 2 times the square root of e. And what we do next is to just multiply everything by -2. So we get y being equal to -2 times the Lambert W of -1 over 2 times the square root of e. And if we go back to what we said y to be equal to, y is equal to e to the power x. So by solving, in order to solve for x, we just say that we just substitute back y for e to the power x. And you'll notice that e to the power x is equal to -2 times the Lambert W of -1 over 2 times the square root of e. So, then, how do we determine if this actually has a solution or not? Now, someone might be thinking that this is, we have a negative sign here, so of course it's going to be a complex number, but that's not the case. For example, Lambert W of -1 over 2 times the square root of e can in fact be negative as well. In which case we actually only potentially have one real solution, since in that case the zeroth branch wouldn't work, since we would be taking the natural log of a negative number. But let's see actually what happens. Is -1 over 2 times the square root of e less than 1 over, or -1 over e? Since if it's less than -1 over e, then it's going to be complex. So we can just compare these two. If we multiply by e, we get we get negative square root of e over 2, and we're comparing that with -1. So negative square root of e over 2. Well, square root of e, it's less than 3, and as such it must be less than 2. So it will mean that negative square root of e over 2 is going to be less than, or it's going to be greater than -1. So in other words, negative square root of e over 2 has to be greater than -1, because square root of e over 2 is less than 1. In other words, -1 over square root, or -1 over 2 times the square root of e has to be greater than -1 over e. And that's great, because -1 over 2 times the square root of e is indeed less than 0, and because we have proven that it's greater than -1 over e, it must be between the interval 0 and -1 over e. And as such, we actually have a solution. But it's only one, since the zeroth branch, as we said here, you might notice that the zeroth branch actually doesn't have any negative solutions. I don't think, at least. Or, actually, I don't know. But, no, actually, I think, no, it doesn't have any solutions, I don't think. But, for that reason, the zeroth branch in this case will not work, because if we take the zeroth branch, we will know that this is a positive number, and in turn this entire value will be negative, and the natural log of a negative number will be negative, or will be complex, and we want to avoid complex solutions in this case. So we're just going to include the negative first branch, because it gives us negative solutions, and as such this expression will in turn be positive, which is indeed allowed for natural log. So x is equal to negative 2 times the Lambert W, the negative first branch, so -1 over 2 times the square root of e. And that's going to be our only real solution, since we have said that the zeroth branch won't work, since it will give us some type of complex solution which we don't necessarily want. So that's one way we can solve this equation. And I'm probably just going to end it off with this question, since it took quite a bit of time. But yeah, I suggest actually searching up for some of these types of questions. There are definitely a lot of them on YouTube that I've managed to find. And if you actually manage to stumble upon them, then I suggest actually giving them a try, since it actually helps with kind of understanding the process of algebra, since it's actually quite tricky to manipulate in an expression in a way such that we get the same expressions, such that we get something of this form, for example, where we have the same expressions for the coefficient, I can say, or the multiplicative term, as well as the exponential term. So when it comes to solving these non-standard exponential equations, you have to be wary of actually being able to manipulate expressions such that you have something of this form. And it becomes a little troublesome if you don't have a constant on the right hand side, since then you would have to take the Lambert W of an expression with an unknown, and that's actually pretty difficult to solve. But to leave it off at that, how about I challenge you to solve this equation: Lambert W of x is equal to x. So this is going to be the question that I'll be giving before saying goodbye, since it's actually pretty interesting if you know what you're kind of doing. And it's actually not a very difficult equation, since it just requires some bit of manipulation, but as long as you know the trick, you will be able to solve this pretty easily, I would think. But that's going to be it for today. I hope that you learned much about the Lambert W function, and I hope that you've been able, or you're going to be able to solve new types of equations using this. But yeah, thank you very much for watching, and I'll see you in the next video.